In terms of organization of the periodic table, there's a couple of things we've already talked about. The first being the atomic number, so we know that all the atoms are arranged according to atomic number. We also know that because the atomic number equals the number of electrons, there is an electron configuration arrangement that we associate with the organization of the periodic table. How we came to that is a little bit of the history behind it. Ultimately, one of the things that you've already begun to discover is that elements in the same group have similar properties. So we know that similar chemical properties. We know that the sodium and potassium behaved similarly. We know that the calcium and the magnesium behaved similarly. And so because of that similarity in property, we know there's something going on with how the elements are organized. The first person to come up with that organization was actually Mendeleev. Now, the main reason we focus more on Mendeleev than Meyer is because Mendeleev made predictions with his periodic table. And what was cool is his predictions involved these two elements, gallium and germanium. So one of the things you have to understand is there were about 64 elements known when Mendeleev made his table in the 1800s. And he figured out that if he arranged elements according to mass, so he focused on mass, if he arranged them in mass going across the periodic table and then periodically restarted a new row, and when he restarted that new row he organized them so that the same column, those elements in the same column had similar properties, he started seeing the organization of the regular repeating patterns. And it was those regular repeating patterns that allowed him to predict what germanium and gallium would be, what their properties would be. And he called these Eka aluminum and Eka silicon. And the remarkable thing was that he was almost dead on. He predicted exactly the properties that germanium would have before it was ever discovered. Now, the second person that we care about in terms of organizing the periodic table is Moseley. And Moseley is who figured out the atomic number, because at the time they didn't know about atomic number. And he figured out the number of protons, and that if you arrange the elements by atomic number, that then when you look at it, all of the columns then match up. And this actually took care of Mendeleev's problem with mass, because if you look at mass, argon actually has a greater mass than potassium. And so because of that, there was this little hiccup in his table. But as soon as Moseley arranges all of the elements according to the atomic number, those hiccups were taken care of. So now we see that we have increasing atomic number from left to right, and that if we repeat that periodically, that we have all of these columns line up and we see predictable chemical properties. So before we go into the families, the first thing we want to go back through is a review of the electron configurations. So we know the S block. The S block, remember, in the first column everything is S1, in the second column everything is S2. So when we look at that, the first two families, which are the S block metals, the alkali metals and the alkaline earth metals, notice that we put this little N in front of it. Okay, so that's referring to if I'm in second row, third row, fourth row, fifth row, I can have 4s1 or I can have 5s2, and I see the same basic electron configuration. So everything in column 2 has an S2 configuration. Remember that this is the final location of the electron and everything below that is full. So when we look at the S block metals, there's a couple of things that are really important. They are highly reactive. You saw this in the lab. They also have what's known as low ionization energies. An ionization energy is basically the energy to remove an electron. So if they have a low ionization energy, it means it doesn't take a lot of energy to remove electrons from these elements. They readily lose those electrons. They also tend to have low densities and low melting points. The other thing you should have noticed is they were very soft metals. I could easily cut it with a scalpel. The differences were also what you observed in that they behaved the alkali metals behaved exothermically when they reacted with water. The alkaline earth weren't quite as exothermic, but they all behaved the same way in that they reacted with water, producing hydrogen gas. Now the next group we're going to look at are the transition metals, and that's these guys right here, what we call the D block element. The D block elements are what we typically think of as metals. They are good conductors of electricity, they have high luster. In other words, whenever you think of all of the characteristics that describe a metal, we're usually describing D block metals, not the S block metals. In addition, the D block metals are a little less reactive, which you saw with copper. They always form colored compounds, as you can see here, and they also have a very unique property in that the atomic size is constant. They form the brightly colored compounds, which we just talked about, but they also form multiple ions. Multiple ions, apparently I can't spell. For example, iron can exist as both 2+ and 3+. And the great thing about being highly colored compounds is we get highly colored solutions out of them as well. Now, the P block elements are everything that's to the right. So we're talking all of these guys here. Now, again, go back to the periodic table. The P block has what we consider nonmetals and metals. So we see a transition from metals to nonmetals in each family, each column. And that's where we talk about the staircase here. And along the staircase are the semimetals. And the semimetals or metalloids actually have properties of both metals and nonmetals. And so we see this variation in terms of non-metallic to metallic properties. In addition, though, just like what we saw with our other blocks, we also see this group configuration. So if you look at each group, they all had to have NS2 because we know to be in the P block, everything below has to be filled. And so in the first column we have P1, in the second column P2, and the third column P3. Remember, we went through and we talked about how you can predict an element's configuration by its location, especially in the first 20 elements. And these guys tend to be harder, denser. This is where we find lead, this is where we find tin. So we can see a lot of those properties. When we deal with the nonmetals, they tend to be brittle. Most of them are solids except for nitrogen, oxygen, fluorine, and chlorine. Bromine, in fact, is the only liquid one. And when we talk about chlorine, fluorine, and bromine, those are all our halogens. Notice our common group configuration. The halogens, the name comes from being called salt formers, so we find the halogens combined with a lot of our alkali and alkaline earth metals in the earth as solids, and we know that they are salts. Now the last column is our noble gases. The noble gases, again, in S2 and P6, they have what's known as a full valence. Remember that the valence was the outermost, so we're looking at the greatest, the largest number. The N just refers to that orbital level, 1, 2, 3, 4, 5. And so with the noble gases, one of the reasons they were the last elements to be discovered is because they don't react with anything. They are what's known as inert. Now the last group of the periodic table we're going to deal with is what's known as the F block elements, and that's these. And the main thing I expect you to know about the F block is two things. One, they're virtually interchangeable. If you've seen one F block element, you've pretty much seen all the F block elements. Second thing is that the actinides, which is the second row of the F block, the 5F, those are virtually all radioactive. So that means ultimately when we look at the periodic table here, we have a trend from left to right and top to bottom. We see mostly metals on this end, and that trend is from a metallic character to a non-metallic character. So we have this diagonal trend going along, and this has to do with everything that we associate with a metal: luster, ductility, malleability, readily losing electrons, to nonmetals which readily gain electrons. And that's seen by this term of electron affinities. And all electron affinity means is they like electrons. So by the time we get to the halogens, they really like electrons. And the alkali metals really don't. So that's why these guys so readily react. And this is the most reactive nonmetals, but they react by taking electrons. These guys react by losing electrons. So that's how we see this change across the periodic table. This is also seen in terms of the electron configuration, because even though the first 20 are the only ones that are truly predictive, remember that it's really the D block elements and the F block elements that mess up our predictions. The S and the P are always right on. So if we have an element in the P block, we know exactly what its electron configuration is. If we have it in the S block, we know exactly what its electron configuration is. Remember, it's only the D and the F that we start seeing the ability to predict kind of break down. So if I know where that element is, I can know how it's going to behave because I know the general properties of that family. So here's the first of 3 questions. Pause the video, read the question, answer the question. When you play, the answer will be there along with what should have given away the answer. So here you should have picked up on poor electrical conductivity. You should have seen that it was brittle in the solid state, good insulator. It's a non-metal. Those are all metallic properties, are the opposite of the metallic properties. The kicker, though, is this idea of containing 4 or more electrons in the outer shell. So let's look at the electron configuration table again. And so by that, notice that it's 2s, 2p, 3s, 3p, 4s, 4p. So that's what we mean by the outermost. It's the greater number. And notice that the s and p are always the same number and the d's and f's vary. So if I have 4 or more, that means I have these 2 plus 2, and I'm at the very least, over on this part of the periodic table, which means I'm dealing with nonmetals. Here's the second question. Remember to pause the video. So this is the very point of all of this that we were talking about. If they have similar chemical properties, they have the same number of valence electrons, and this ties back into what we just talked about with where they are in the periodic table in the s and the p valence. And the last question, pause. If I'm going to show the most metallic character, that means I want to be down here at the bottom and left of the periodic table. The only element that is down at bottom and left is cesium.